Imagine capturing the perfect moment with your camera, but then wishing you could just tweak one of the lights in the scene, maybe make it warmer or brighter.
Yeah, normally that kind of control just vanishes the second you take the picture, right? The light's fixed.
Exactly. Your standard photo editing tools, they let you adjust overall brightness, maybe colors, but they don't give you that kind of, precise command over individual light sources.
It's like trying to adjust the volume of just the violin in a full orchestra recording after it's already mixed. It's tough.
Okay, let's dig into this
Hmm.
because this deep dive, it takes us into a really innovative research paper. What they've developed is a method to achieve exactly that. Fine-grained sort of parametric control over individual lights in a single image after you've taken it.
Right. Think about it adjusting the intensity, the color of a lamp, almost as easily as if you were still standing there setting up the shot.
And the really exciting part, I think, is that it doesn't rely on having, like, multiple photos of the same scene.
Or needing to build a super complex 3D model of everything. It's a more direct way, almost intuitive, to relight an image, which honestly was previously only possible with really high-end graphics software or, meticulous on-set work.
Precisely. So our mission today is to understand how this new diffusion-based method manages to pull this off and what doors it opens up.
Okay.
Our guide is the research paper itself. It details their whole process, gathering data, both real photos and computer-generated images,
Right, the synthetic stuff.
the inner workings of their diffusion model, and the results they got, which are pretty compelling. They've got some really striking before and after examples.
Yeah, those visuals help a lot. It feels like for the first time we might have a relatively accessible way to get that lighting control you'd normally need 3D modeling for, or, just being there during the shoot.
To really get why this is a big deal, let's think about light's role in a photo. The paper points this out well. Changing a light source isn't just about brightness.
No, it affects everything. The sense of depth, contrast, where your eye focuses, and light color. That's huge for mood, right? Warmth, drama, a cool clinical feel.
Totally. When we're actually taking a picture, we're doing this stuff instinctively, moving lamps, using reflectors,
All happening as you capture the scene.
but trying to get that same level of control afterwards with normal editing, it's a massive challenge. The paper mentions the old way, building a full 3D computer model of the scene.
Which is just incredibly detailed work, not feasible for your average photo.
So what's fascinating here is how they found a different path using these things called diffusion models.
Right. Now, for anyone not super familiar, a diffusion model is basically a type of AI that learns to understand the structure of data. In this case, images with different lighting.
And then it can generate new data that fits that understanding.
Exactly. Think of it like the AI learns the subtle patterns of how light behaves, bounces, shadows, highlights, and then it can recreate those patterns in new ways following instructions.
Okay, here's where it gets really interesting. They didn't build this model from scratch.
No, they fine-tuned an existing one, which is smart.
And their training data, the stuff they fed the model to teach it, is this really clever mix. A smaller set of real photos, and then a much larger set of synthetic computer-generated images.
We should definitely talk about how they got those photos.
We will. But first, the key insight the paper mentions is leveraging the linearity of light. Sounds technical, but what does it mean here?
It basically allows them to create training data, especially the synthetic kind, that shows very precise, controlled changes. Like just changing the intensity of one specific light, or just its color, or even just the ambient light filling the room.
Ah, okay. So it helps isolate the effect of each light source?
Pretty much. And that moves us beyond simple brightness sliders. It lets you fundamentally alter the mood and focus after the fact. That's the dream for photographers, right?
Absolutely. Okay, so let's dive into how they got those real-world photos first. They collected about 600 pairs of raw images.
Using standard mobile phones, interestingly enough, mounted on tripods, though, for consistency.
And the crucial bit was capturing the exact same scene twice.
Huh.
Once with a specific light source turned on, and then again with it turned off.
Simple but effective, and they used the raw image data, the unprocessed stuff from the sensor, to do post-capture calibration.
Why raw data specifically?
Well, it contains more information about the light levels. It helped them ensure the images were properly exposed, which is really critical if you want to accurately analyze how the light changes between that on and off shot.
Makes sense. So they use the off image as the baseline, the ambient light. They call it IM.
Right, and then to isolate just the effect of that one light, they subtracted the off image from the on image. That gives them eye change.
The change image. Now, they mentioned sometimes this subtraction resulted in slightly negative values.
Yeah, likely due to tiny fluctuations in ambient light, maybe sensor noise, calibration quirks. To avoid accidentally making parts of the image darker when they shouldn't, they just clipped those negative values, set them to 0.
Okay. And then they expanded this data set. 600 pairs isn't huge for training AI.
Right, they did some clever augmentation in post-processing. By tweaking the brightness and color of the light effect in those original pairs, they multiplied their dataset by about 60 times.
Wow, so ending up with around 36,000 images from the real-world shots.
Exactly. And the paper stresses why having this real data is important. Real photos have subtle camera artifacts, lens distortion, specific sensor responses, things often missing in purely synthetic images.
So the real data helps the model learn to make changes that look, well, real, and avoids it getting too tied to the maybe cleaner look of synthetic images.
Precisely. It helps disentangle the lighting change itself from the style of the renderer.
Okay, now let's talk about the synthetic side. The computer-generated power. They use a much larger set here.
Yeah, about 600,000 images generated from 3D indoor scenes using Blender. They started with 20 different basic scene layouts.
And they went wild with randomization.
Pretty much. They varied the virtual camera's viewpoint, the virtual light's properties, intensity, color temperature, size, angle. They even randomly placed new virtual light fixtures into the scenes.
And varied the overall environmental lighting, too.
Yep, different environment maps, different background illumination. The goal was lots of variety within those 20 base scenes.
And just like with the real photos, they rendered these synthetically with the ambient light separate from the target light source.
Correct. Rendered them separately and combined them later. Gives them that clean IM and eye change separation again. They also did something smart during rendering. They limited extreme pixel values
Why is that?
to avoid getting overly noisy or weird results after tone mapping, which is that process of converting the rendered image into something that looks good on a normal screen.
Got it. So even though the paper admits the synthetic data might lack diversity in, say, object shapes or materials compared to the real world,
Its strength is teaching the model the underlying physics. How light should behave consistently, plausibly, across different views and conditions. That's hard to get just from limited real data.
okay, so we have this model trained on this mix of real and synthetic data, understanding IM and eye change. How do we, the user, actually control the light?
Well, the model has learned how changes to those IM and eye change components affect the final look. So it can now accept parameters from you to control the target light's intensity and color, and also the overall ambient light.
How does the color change work?
They use something called change coefficients, see, in linear RGB space. Basically, they figure out the light's original color and then apply math based on the color you want to transform it.
And they have a formula for the final relit image, iRelit.
Yeah, it combines everything.
Yeah.
How much you want to adjust the ambient intensity, alpha, how much you want to adjust the target light's intensity, gamma, the desired target color, CT, and those IM and eye change images we talked about.
It sounds like a neat mathematical package for the whole process.
It is. And they also consider tone mapping. You can either keep the exposure fixed across edits or let the system adjust it for each change. And interestingly, you tell the model which strategy you're using.
Ah, so the tone mapping choice itself becomes an input, another control.
Exactly. More control over the final look.
Okay, let's shift to the tech side a bit. How did they actually build and train this? They mentioned fine-tuning a latent diffusion model.
Right. Similar in structure to something well-known like Stable Diffusion XL. Latent just means it works on a compressed version of the image, which is more efficient.
And fine-tuning means they're starting with a model that already knows a lot about images.
Yes, it's already been trained on tons of general images, so it has a strong foundation of what looks realistic. They then trained their specific version for 45,000 steps, which takes significant compute power. They use TPUs, specific learning rates, batch sizes, working at a Honto and 24 by 124 resolution.
And how do you feed the specific instructions like change this lamp to blue into the model that's conditioning, right?
Correct. They use both localized and global conditions. Localized applies to specific areas. This includes the input image itself, a depth map.
Which tells the model about the 3D shape of the scene.
Exactly. Also, a mask showing which light source you want to change, how much you want to change its intensity, and the target color you want. It's like giving the model a detailed map and instructions for specific pixels.
And these get processed and fed in.
Yeah. resized, maybe some math applied, then combined and fed into the model.
What about global conditions, things affecting the whole image?
That includes the overall change to ambient light, just a single value, and that tone mapping strategy we mentioned, like a switch, 0 or 1. These are encoded differently and influence the model through something called cross-attention.
Okay. And they mentioned sometimes randomly dropping some conditions during training, like the depth or color info.
Yeah, a clever trick. It makes the model more robust, allows it to make reasonable changes, even if it doesn't have all the specific inputs later on. They call it unconditional inference.
They also focused the training intensity changes on the simple on-off case.
Seems like it. Sampling intensity changes with a bias towards fully on or fully off, which is a very common use case, turn a light on or off.
Makes sense. So the big question, how well does it actually work?
Well, they used standard image quality metrics, PSNR and SSIM.
Okay, the objective numbers.
Right, comparing the output to a ground truth where possible. But honestly, the visual results and the user studies they ran are maybe more telling.
What did the user studies show?
People generally preferred the results from their method compared to other existing relighting techniques they tested against. That's a good sign.
And the applications they showcased sound pretty cool. Adjusting intensity and color, obviously.
Yeah, like turning a warm street lamp cool white. They also showed applying edits one after another.
And the non-photorealistic stuff, changing lighting in a cartoon.
That was fascinating. Shows the model learned something quite general about light, not just photorealism.
Also, consistent lighting for animation.
Very promising. Imagine relighting an animated sequence easily and inserting new lights without needing geometry. They showed placing a light source marked by a red X.
That hints at some serious creative potential, doesn't it?
Absolutely. But to their credit, they also discussed the limitations. It's not perfect yet.
Like the model being biased by its training data, the candle example.
Exactly. It saw mostly certain types of lights, so when asked to relight candles, it kind of treated them like fluorescent tubes. But it did handle other things well, like turning off a paper lantern or lighting a desk lamp in that cartoon. So it depends on the light source type.
How about reflections? That seems tricky.
Surprisingly, it often did really well, relighting a chandelier reflection in a mirror accurately, maintaining reflections when the source changes, even adding or removing those bright specular highlights on shiny things.
But there were some failures.
Yeah, particularly with perspective issues in some images. Probably because the training data was mostly indoor scenes. Looking straight down a long outdoor path, for instance, could cause problems. They show more examples, good and bad, in the supplementary material.
Okay. And other limitations. They mentioned the mobile phone capture.
Right. Practical for gathering data, but it means the relighting isn't in precise physical units like lux or lumens. It's more perceptual.
And a slight knowledge drift, because the real and synthetic data aren't perfectly matched.
Yeah, a subtle domain gap that can sometimes introduce minor artifacts, things future work could address.
So despite those limitations, the takeaway seems pretty significant. This is a major step forward in controlling light after the fact.
Definitely. It unlocks creative options that were just incredibly difficult or impossible before for most people. That mix of real and synthetic data seems key to their success.
Absolutely. And while there's room to improve broadening the data set, maybe refining capture, this really feels like a glimpse into the future of image editing.
For sure.
So as you think about this, just consider, how could this kind of tech change photography? Or filmmaking, or even just how you interact with digital images day to day? What new art forms or practical tools might pop up when manipulating light becomes this flexible?
It really does spark the imagination about what's next.